Okay, so let's continue. Last time we solved this Gorkov-coupled equations for this diagonal Green's functions, G, and off-diagonal Green's functions, F. And once we Fourier transform this Gorkov-coupled equation for the Green's functions in this BCS state, we could get the solutions, which is given by these two expressions. This G as function of this Q, three-dimensional vector, and the frequency Q0 could be expressed in terms of these factors. In the numerator, we get minus IQ0 plus epsilon Q, where epsilon Q is the free electron kinetic energy. And in the denominator, you get Q0 squared plus this Bogoliubov excitation capital EQ squared, whereas EQ is defined as the square root of this free electron kinetic energy relative to the Fermi energy, and you square that plus your square of the gap function. And this F, which is the off-diagonal Green's function, is proportional to this gap, delta, divided by, again, the same denominator, Q0 squared plus Bogoliubov excitation energy squared. So this is our solution. And all these calculations that you could do are based on the solutions. For example, if you could calculate this transport or conductivity or whatever properties that you can imagine, and the only thing that you need is this Green's function, G and F. So later we'll see that this Green's functions, G and F, could be combined into the 2x2 matrix and in a so-called Nambu basis. And then you could generalize this Green's function in the BCS states in terms of this 2x2 matrix, G and G, F, F star. So once you know the Green's functions, 2x2 matrix, you know everything. Okay, right? So we will come back to this in just a moment. But let's just rewrite this G and F Green's function in more kind of a conventional form, where you could use the simple pole function and to actually re-express this G and also the F, and then multiply by so-called the coherence factor, U of Q and V of Q. So this U of Q and V of Q are called coherent factors of the BCS state. Namely, they are related to the probability amplitudes of forming a Cooper pair or not to form a Cooper pair. Okay, so the precise definition or interpretation of these coherent factors can be found in our earlier lecture notes in the previous semester. So if you remember this advanced solid state 1, and we have defined such coherent factors back then, so I won't repeat that, but this is a convenient way to rewrite this Green's function G and F, because you know very well that if you perform some kind of a contour integrations and for G or F, you know immediately what you get, because there's a simple pole right here, and when you pick up the pole, when this imaginary part or Z hits this E of Q, okay, and you could pick up the residue, and the residue is nothing but this U of Q squared or V of Q squared. Here, this U of Q and V of Q squared are defined in this way. So if you could look at this one more time, then you will find that when there's no superconducting behaviors in your system, namely if your gap vanishes, then this capital E is reduced to epsilon E, epsilon Q. When that happens, when you are back to the normal state, then the U of Q is actually what? 1/2 times 1 plus 1, which is 1, right? But what is the V of Q, which is 1/2 times 1 minus 1, which is 0. So you immediately find this correct interpretation of this coefficient U of Q and V of Q is that V of Q should be the amplitude, the probability amplitude to form a Cooper pair, because if you turn off this gap, you don't have the superconductivity, and then V of Q vanishes. Okay? And so U of Q should be the probability amplitude not to form Cooper pair. Okay? And you know very well that there's a so-called Bogoliubov transformations taking you from your physical, say, normal state electron operator to the so-called Bogoliubov operators. Okay, something like that. So you could check your lecture notes. So in the BCS state, actually the gamma, which is a Bogoliubov quasi-particle operator, is the operator that diagonalizes this Hamiltonian, the BCS Hamiltonian, and which is linear superposition of C and C dagger. Okay, of course, you need to take care of this momentum indices of these two operators. Okay, so any case, so this is the four solutions of this BCS Green's functions. And so let's just go back to the self-consistent gap equation. So remember, this delta is nothing but what you sum over this Mossbar frequency of this f. All right? Okay. So let me just transform this to the integral equations. Okay, this is the case because you know what this f is, right? Okay, so the only thing that you need to do is to do this Mossbar sum and also this momentum integral over this off-diagonal Green's function f. Then you get this gap, right? So the gap is nothing but you sum over Mossbar frequency and momentum vector q of this f off-diagonal Green's function multiplied by this coupling constant g. And this is called the BCS gap equation. And this is so-called integral equation because on the left-hand side and right-hand side of the equation, you get delta appearing, and also delta is hidden in this Bogoliubov excitation spectrum. Remember, this E of Q is given by this. Okay, so for non-zero delta, you can actually cancel this delta with that delta on the other side of the equation, because delta is simply just a constant, independent of momentum or frequency, so you could very safely just cancel this. But you also have that delta factor hidden inside this Bogoliubov excitation spectrum, so that you need to really perform such a self-consistent equation and to look for a solution. So next, we will try to solve this BCS gap equation and look for the gap as function of temperature, both below or above Tc, or when temperature approaches 0. Okay? And by the way, we have determined this Tc already from this Cooper instability. Remember, when this Cooper instability happens, this ladder diagram diverges because the denominator becomes 0, and the condition that the denominator vanishes is precisely when temperature hits this Tc. Okay, so you got this kBTc is what, 1.14 times what? This factor, I don't recall, but you can find it out. The gap, right? So the kBTc, 1.14 the Debye energy times e to the minus this lambda 0 times density of states, inverse of that with a minus sign exponent, and we will recover this by solving for this solutions of this BCS gap equation. Okay, so either way. And more than that, we could estimate temperature behavior of the gap, especially below Tc, or when T is approaching Tc, or when T is very, very small. Okay, so you see that you could make a plot of this gap against temperature, and you get this behavior. All right? Okay, so let's take a short break. This is standard, but later you will find out that this Green's functions in the BCS state that we just obtained are really, really useful, because you can imagine that you like to calculate the transport of supercurrent and this magnetic susceptibility and so on, and this is the only way. Okay? So even if you can solve this, say, Bogoliubov excitation spectrum, but to really calculate this transport, you do need both Green's functions. Okay, so knowing this Bogoliubov excitation spectrum is not enough. Okay, so you really need the Green's function in order to calculate something that can be measured in your laboratory. And that Green's functions are precisely the reason why we need to learn this technique. Okay, so let's solve this gap equation. Okay, so let's convert this BCS gap equation in terms of the energy integration over the epsilon, where epsilon is the electron kinetic energy relative to the Fermi level, And inside the integrand, it is 1 over this square root of epsilon squared plus delta squared times hyperbolic tangent function, which we have encountered already when we deal with the Cooper instability. So to solve this integral equation, we could start from this easiest part where this temperature is really close to the transition temperature Tc minus. So we approach this Tc from below. So in that case, when T is really close to Tc, this gap really tiny, right? So we assume that delta is really small, and as a result, we could Taylor expand this function, the integrand, in terms of powers of delta. Okay, so this is, this first few terms in the leading order in delta. Okay, so then we could simply just try to perform this Matsubarra sum for this, say, first and second term, and let's see what it gives us. So when we did this Matsubarra sum, we get this. Okay, so this will be the first term, right? So when you do the Matsubarra sum for this first term, you get this. And for the second term, you get this. Okay, so you could check details in your textbooks. And so I neglect all the other higher order terms, including this delta to the power of 4th. So I only keep this first two terms. Okay, so let's just do this. When temperature is really close to Tc, delta really vanishes. Okay, so you can determine Tc based on this condition that when T is exactly Tc, then delta vanishes, so you don't have the second term. The second term goes away because delta is 0 right here. So you have only the first term. So when that happens, T should be replaced by Tc. Okay? And then you could get precisely what we have before. Okay, so this integral is precisely the same integral that we evaluated before when we discussed the Cooper instability. So this is precisely what we have. And so you get the same results. All right? Okay, so what's next? Well, of course, we know the relation between Tc and this coupling constant G times this density states. So we could rewrite this gap equation by plugging this, this relation right here, that we could replace this G times density states and 0 by the function of kBTc. Okay, so we could plug in this information back here, and we can rewrite this BCS gap equation in the following form. So we could eliminate G times N0 by this kBTc formula you get. Okay, so when you plug in this result back to this gap equation, and again, you could plug in here, okay, and then you could perform the similar integrals like we wrote here, and then you could sum over this integer n here from 0 to infinity of this 1 over 2n plus 1 cubic term right here. So, and this is the term when you sum over Matsubarra frequency, Q0 of this term. And when you do so, you find that this is nothing but this Riemann zeta special function, zeta of 3 times 7 divided by 8. Okay, so this is a special function, and so you could plug this in here, and you get this gap as function of temperature. So what you get is this. So for temperature, it's close to Tc, but below Tc, and you get a square root behavior of the gap, which means that the gap vanishes in a square root manner, and that's what I plotted just a moment. So this is Tc. So this function right here is proportional to Tc minus T square root. And experimentally, this BCS predictions agree very well with experimental data. Yeah, so this is a success, one of the remarkable success of the BCS theory, that we can predict this BCS gap as a function of temperature. So we finished this one part of this gap equation. We know the gap is a function of temperature close to Tc. So what happens for this gap as a function of temperature when temperature is really, really tiny? Meaning, what is the behavior of the gap? We'll be right here when temperature is really, really small. And we could also get some kind of a approximated form for this gap when temperature approaches 0. But in general, we don't have a exact analytical solution for the gap function, but it is not a difficult job to evaluate this gap equation numerically. Okay, so let's take a short break. When we come back, let's address this gap, the low temperature limit. So the remaining part of this lecture is to finish all this BCS calculation. For example, to make a link of this Nambu formulation of this BCS theory, and let's write down this 2x2 matrix representation of the Green's function, as I mentioned a few minutes ago. And based on this 2x2 Green's function matrix, we could calculate this transport. For example, this conductivity in a superconducting state. And we will refresh our memory regarding the Kubo formula and write down this current correlation function. And then in the BCS state, we should plug in this 2x2 Green's function matrix, and then you could evaluate this or the transport in the BCS state. So this is something that you could learn, and there's no other way that you could calculate this transport in the BCS state without using the Green's functions. Okay, so let's finish the job. So when temperature is really small, which approach 0, and you could also solve this gap equation and get this approximated form, which is some kind of a constant minus exponential function of delta 0 over kBt, where delta 0 is defined as the gap at 0 temperature. So this may appear in your final exam. Okay, so you could check all this reference for this part of approximated form when T almost vanishes. So, but what about delta 0? Delta 0 is the gap at 0 temperature, and when temperature is really 0, hyperbolic tangent function becomes 1, so you could very easily evaluate the 0 temperature limit of the gap equation like this, and this integral is very easily solved, and you get this log function of the inside log. You get this phonon Debye energy, right, divided by delta 0. So you invert that relation, you get this energy gap, which is defined as 2 times the BCS gap to delta, which is given by this expression right here in relation to this Debye energy and this e to the minus 1 over g times density of states. But you know very well that kBtc also has very similar relations with the Debye energy and also this exponential factor. So you could take the ratio between this energy gap, capital EG, to this kBtc, and you get the universal constant, 4 divided by 1.14, which is 3.5. Okay, so this is the original BCS prediction for ordinary metals when they become the superconductor. And you can measure this energy gap between the lower branch of the Bogoliubov and upper branch of the Bogoliubov quasi-particle band, and you get 2 delta. And you know what Tc is. You take the ratio, you get the universal constant. Okay, ratio. And most metals have this ratio between, say, Eg and kBtc around 3 or 2 to 5, 2 to 5. So you take the average 2 plus 5 divided by 2, which is exactly 3.5. So this prediction agrees very, very well with the experimental observations on many metals when they become superconducting. Okay, so this is a great success of this BCS theory because this is a really naive assumption that the delta is just a constant independent of frequency and momentum, and you get the attractions potential, which is, again, S-wave-like potential. Okay? So the S-wave superconductor within the BCS theory really is remarkable when you apply the theory to explain these ordinary superconductors. So this is for today. Okay, so tomorrow we will finish our semester's lecture by computing the Kubo formula for the electrical conductivity in the superconducting state. Namely, we should refresh our memory on this, say, Kubo formula and the current-current correlation function. But this time, this current-current correlator should be evaluated within this 2x2 Green's function method. And then we're done. Okay, so now you could make a link of our lectures on BCS to this BCS part in the previous semester, Advanced Solids 1, and then I think you get a full comprehensive understanding of ordinary superconductors. So I'll see you on Tuesday, tomorrow.